Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of our unit Mechanical Properties of Solids. So let's begin with today's class. In today's class we will discuss first about the Hooke's law. So let's begin. Before we study the Hooke's law, we need to understand what is elastic limit means. So when we said it's a maximum stress within which a body regain its original size and shape after the removal of the deforming force, this is called as the elastic limit. If the stress developed in a body exceeds this elastic limit, then it will not get the initial or the original size and shape completely, even after the removal of deforming force. So it is the maximum amount of force that you can apply on the object. If you want that after removal of this force my object should regain its original shape and size. If you are applying a force more than that, if you are applying a force more than its elastic limit, then even though you are going to remove the deforming force, it is not going to regain its original shape and size. I hope this is clear. So what Hooke's law says, let's understand. Hooke's law states that within a elastic limit, this is with conditions applied, yes, within elastic limit, the stress is directly proportional to the strain. This is given by the Robert Hooke, who is an English physicist and in 1676 and performed an experiment on spring, and he found that the elongation produced in a body is proportional to the applied force or the load. And then he has given this, that if you are going to do this within an elastic limit, if you are going to perform this within an elastic limit, then force applied, that means stress, is directly proportional to the strain. So if a statement is converted to a formula, then within the elastic limits we can say that it's a stress which is directly proportional to the strain. So this could be written as, if I remove proportionality constant, then I need to proportionality symbol, then I need to put one of the constant. So this could be written as stress is equals to one of the constant multiplied by strain. And when I say it's a one of the constants, so this constant could be the ratio of the stress divided by strain. Let's call it K at this point of time, where K is the proportionality constant and it is called as the modulus of elasticity. And unit of modulus of elasticity, this is modulus of elasticity, this will be equals to stress divided by strain. So stress, it's a Newton per meter square. Strain having no units, so it's a SI unit would be equals to Newton per meter square. It's a CGS unit, it would be a dyne per centimeter square. Dimensional formula, it's an m1 l minus 1 t minus 2. I hope this is clear. Yes, one more thing. If I plot a graph for the stress versus strain, then this could be, look at the straight line having fixed slope, having constant slope. I hope this is clear. Is it clear? Is it clear? Let's look at some quick questions. It's a Hooke's law states that within the elastic limits the stress is blank to the strain. Yes, stress is directly proportional to the strain. It was something like this: stress is directly proportional to the strain, and I have removed this proportionality constant and included the symbol. That constant, sorry, it's a y is equals to stress divided by strain. It is something like this. This is Young's modulus of elasticity. Next, the dimensional formula for modulus of elasticity, it's a stress, this modulus of elasticity, it is the ratio of the stress divided by strain. If it's a stress, let's call it F by A. strain, it's a change in length. Suppose change in length divided by original length. This is dimensionless. This is having force by area. Force, it's a kg into meter per second square. Area, it's a 1 by meter square. So this and this has gone. So this is equals to kg per meter into second square. This is m1 l minus 1 t minus 2. Now let's plot a stress versus strain curve. This is very important for theoretical purpose as well, for theoretical plus competitive examination purpose. Competitive examination purpose. Even if this is not going to be asked in competitive examination, if no question has been asked from competitive examination, it is sure shot for the theoretical questions. Yes, for the theory examinations, this is to be asked. This is going to be asked for sure. I hope this is clear. So let's look at this. What we have done is, let's suppose what we have done is, you can understood it like this, that let's suppose we have a certain road, and on this road, or in this situation, we can put on the loads. This is a container where we can put on the loads, and we are going to removing the loads, and something like that that will happen. So this is the container in which I can put up the loads, and I will observe this object. It's a road having length L. So first, in this situation, what happens is that if I started increasing, initially the initially the weights were only this much, and when only this much weight has been put on, when only this much weight has been put on, its length is started increasing. So you can see this, it is the region from O to A. It is the region from O to A, where this particle O to A, this object follows the perfect elastic behavior. And when I say it follows the perfect elastic behavior, in this it means it's a stress which is directly proportional to the strain from O to A region. I hope this is clear. So this is, we can call as the proportionality. It's a, it's a proportional limit, that up to this, up to the location A, up to the point A, stress is directly proportional to the strain. So what happens next? I keep on adding this weight. Let's make it more understanding purpose. And what the situation was, situation is something like this, that initially this container was empty, and I have put up the weight on it, and it has reached from this to this. Now from A to B, I what I mean is, I keep on adding this weight. If I keep on adding this weight, then from A to B, from A to B, it is that as stress is increasing, strain is increasing, but this is not directly proportional. These are not directly proportional to each other, but this is keep on changing. So if I remove a load, if I remove a load, when I say if I remove a load, that means I am going to remove this all masses from here. Look at this. If I remove all the masses at the point B, then this object will again regain its original shape. That means it will again come back at this position. And if it is again come back to this position, if it is again come back to this position, then we can say that at position B or up to position B, it is behaving like elastic body. That if you remove your deforming force, if you removing your deforming force, then I'm going to regain my original shape. So this is the last point, it's a point B, where it is following elastic behavior, that remove the load, I will regain my original shape and size. So now what we assume is that let's put up the weights one more time, and we started putting up the more weights. Look at this, that this is the build up of the weights, and as I'm going to build up the weights over here, this is again going to start from here to here and from here to here, and then again going to move from point B to C. Now I might thought that at location C it is going to be breakup, but it has not. But now I understand that there might be change in the length. But what happens when I remove the load at point C? What should happen? First tell me. If I remove the load at point C, if I'm going to removing the load at point C, what should happen? the the thing that should happen is that it should reach from C to this point from the point O. But surprisingly it has not regained its original shape, but it is available. It is going to be at this point. That means, if if for the understanding purpose, if your original length is, let's say, 1000 centimeter at O, if your original length is at 1000 centimeter at O, then when you remove the force from point B, then at point B, length was, let's suppose, 1000 plus 5 centimeter. This all are for the understanding purpose. So if you remove the force from point B, now again it will regain length of 1000 centimeter. But if you are going to remove your load from here, but the situation is, a deforming force if you remove deforming force from point C, then then it is not going to regain its original shape and size. Its length will be, let's suppose, 1000 plus x. Ideally it should go to the 1000, but if you see this, it is not at 1000, it is 1000 plus x. So from here it is the point, or it is what we call as the plastic behavior has started. From this, plastic behavior has started, and this is what we call as a permanent set, that now throughout the life of this material it would be at 1000 plus x centimeter. It is not going to came back to the 1000 centimeter again in its life. I hope this is clear. Is it clear? Is it clear? Now, what I understood is that now the material has been wasted because plastic behavior has started and permanent set has been developed. So if it has been developed, then why not to put up more weight, and let's check what happens next. So what I have suggested is that put on the more weights and see this, that what is the situation when this wire, or when this road is going to break down. So this all is the plastic behavior. This all are the plastic behavior of the load, and I keep on put up the weight on here. And as I keep on put up the weight over here, at a certain instance, a situation arrives where this road has been break down, and this is location which I said it's a breaking point. This is the breaking point of this rule. I hope you understand the complete situation. Is it clear? Is it clear? It is very powerful theory. This is clear. This is clear. Are you sure? Are you sure? Do you understand this? So, if large deformation occurs between the elastic limit and breaking point, then the material is known as the ductile. If very large deformation occurs that between elastic limit and breaking point, then we call that material is ductile, such as the copper or silver or gold, etc. But if very small deformation occurs, a very small deformation occurs between the elastic limit and breaking point, then the material is called as the brittle. Yes, it is going to be break very soon. Let's take an example. They are the glass or ceramics. This all are the brittle material. That it is something like this, that if this range, we are talking about this range, this is the elastic limit and elastic behavior and elastic limit. If this range is very short, if this range is very short, then this is the brittle. If this range is very high, then it is the ductile material. Does it clear? Does it? Are you sure? Great. Now let's look at the certain quick questions. The extension begins to increase even without any increase in load or stress. The wire is said to be at, yes, it is said to be at the yield point, where it is going to increase in its length without any increase in the load or the stress. Next, a stress straight line in stress versus strain curve represents, yes, it is something like this. It is O to A. This is the region which we call as the elastic limit, where Hooke's law is valid. Next, the property of metals which allows them to be drawn into thin wires and sheets beyond their elastic limit without rupturing is called as the ductility. Higher the ductility of an object, higher would be their capability to convert themselves into thin wires and sheets. And one more thing, it's a property of delay in regaining the original shape and size of the body even after removing the force on a body, that is known as the elastic after effect. So what happens is that in reality, let's understood the situation that this is a road of length, let's say 10 meter, that means 1000 centimeter. If I'm going to pull it from here, if I'm going to pull it from here, even within a elastic limit, let's suppose this road will become now something like this. It's a lengthwise, it's a 1010 centimeter when I have applied a force. Now if I remove the force, and if I make this force as a zero, then if this is happen, when this is happen within a elastic limit, then it will regain its original shape and size. It is of again 1000 centimeter. Look at this, when force is zero, after removal of force, it is again going to regain its original shape and size. But from this thousand centimeter to 1000 centimeter, it has taken certain finite amount of time. And when it has taken certain finite amount of time, it is, this is known as the elastic after effect. That it is the property of delay in regaining the original shape and size of the body even after removing the deforming force of a body. This is known as the elastic after effect. I hope you understand this. Do you understand this? Have you understand this? Are you sure? Any doubts up till now? Is there anything? Is there anything? No? Great. Now let's discuss the elastomers and elastic moduli. What is elastomers and what is elastic moduli? Let's have a look. There are certain substances which can be stretched to have very large values of strain. That is what we call as the elastomers. If I plot a graph of stress versus strain, then let's understood that if it is having a very high amount of strain. It is having a very high amount of strain. This is the graph of the elastomers. From the graph, it is quite clear that where the elastic region is quite large, the material is not going to obey the Hooke's law. Yes, this is the region that this is the region where if you remove the force, if you remove the force, it will again it will again regain its original shape. So it is within the elastic limit, but it is not following Hooke's law. I hope this is clear. This figure shows the stress versus strain curve of the elastic tissue of the aorta. Yes. Uh, examples of this kind of materials, examples of these elastomers are the natural rubber, synthetic rubbers, a tissue of aorta where the large blood carrying vessel from the heart, etc. So this all are the elastomers, and on all this elastomers having a very large value of the strain when it has been stretched a little. So stress versus strain curve for the elastic tissue of aorta or the present in the heart is the example of the elastomers. Please note that although elastic region is very large, here the material is not obeying Hooke's law over most of the region. Next, there is no well-defined plastic region that from where this is going to be behave as a plastic material, that if I remove the deforming force, and it will start behaving as it is a plastic body. We don't know. Or substance like tissue of rota or the rubber, etc., which can be stretched to cause a large strains, are known as the elastomers. Please remember this graph. This is favorite to the examiners. This is going to be asked. I hope this is clear. So is it clear? Is it clear? Are you sure? Are you sure? Do you have any doubts in this? Is there any doubts? Anything? Anything? Are you sure? Are you sure? Now let's discuss one of the more conceptual point. That is what we call as an elastic fatigue. It is the elastic fatigue. So when a body is subjected to a repeated stress, even within the elastic limit, it becomes weak since it loses its elastic property to some extent temporarily. This is what we call as an elastic fatigue. So if you have observed it that it is something like this. Let's suppose this road is there, and it has been applied a certain amount of force like this, that if I hung a block to this road, that means I'm going to apply a force because mg is acting by default. So what happens that if this wire or if this road is going to be used every time, every time at repeatedly, then there is certain uh, permanent change in the shape will be found if I'm going to use this repeatedly even within the elastic limit. So what generally in the labs have been used, they have a different set of routes. First they are going to use it to perform certain experiment, then they will keep it aside and they are going to use a different route to take a same observations, and this can be done smoothly. Once if I have used this rows for this day, on the very next day I'm going to start with this. It is the same thing that if you are living in the apartments, and if lifts are there, if it is a very high rise apartment, then you might have observed that we generally have two lifts, and one of the lifts work for the 12 hours and another lifts works for the another 12 hours. So it is the mechanism to not create elastic fatigue, because what is left basically, it is having the cables only, and that cables are behaving as the properties of solids as well. So when we use this cables for a certain 12 hours, then we are going to provide it rest. We are going to provide it rest, and we are at when this is at a rest, this is going to work, and when this is going to rest, this is going to work. So we are switching it in a 12 hour shift. If you have gone through the labs, if you have gone through the labs, now maybe schools are open, and if you are an 11th class kid, then you will get a chance to go through the school labs. You will find that at that time a springs well there, where you are going to apply a certain amount of force by hanging certain blocks having a mass m. So your lab assistant sir or ma'am will teach you that if you have used this spring at this time, then the next batch or the next time you are going to use some another springs. Yes, so let's call this as a spring 1, and let's call this as a spring 2. So both are of made up from the same material, both are of same length. That means their spring constant K would be the same. So when this is going to be used, when any one of the spring is used, this is working. At that time it is at rest. If you have been arrived at the next batch loss, then it is might possible that this is working and this is at rest. This all are the mechanisms. This all are the mechanisms to reduce the effect of elastic fatigue. That means if you are pulling anything, if you are stretching it anything even within the elastic limit, if you are doing it repeatedly, it is going to lose sooner or later its elastic property. But if you have provided it a certain amount of rest, basically it is a time basically it is a time to realign themselves. So thus it is working. It's an elastic fatigue. I hope this is clear. Is it clear? Is it? Is it clear? Are you sure? Are you sure? Great. Now let's discuss a very important topic. It's a breaking stress. The breaking stress of a wire is the maximum stress at which the wire breaks. So basically breaking stress is the breaking force divided by area of cross section. First, breaking stress depends on the nature of the material of the wire, or I should say this, it is the materialistic, or it's a material dependent property. It is the material dependent property. When I say material dependent property, that means if two aluminum wires have been taken, maybe of different dimensions, that let's say this is the first aluminum wire, length is L1, cross sectional area A1, and this is another aluminum wire. As you can observe is that length is different, cross sectional area is different, but breaking stress of first wire would be equals to breaking stress of second wire if material is same. If they have been made up from the same material, that means that breaking stress is equal. So if breaking stress is equal, it depends only on the nature of the material of the wire, and it is independent of the length and area of cross section of the wire. I hope this is clear. It is independent of the length and area of the cross section of the wire. So a very long wire suspended vertically may break due to its own weight. The maximum length of a wire that can be hung without breaking under its own weight could be written as, it's a breaking stress which is equals to mg divided by a. If I write mg, it's a density is equals to mass by volume. So mass can be replaced as a density into volume, while volume can be replaced as the area into length. So if I replace mass as equals to density into length into area into g, divide by area. So this area and area has been gone, and I have been left with the L rho G. This is breaking stress. So this would be the maximum length. This would be the maximum length of a the thicken wire that can be hung without breaking under its own weight. I hope this is clear. One more very important parameter is that when I say it's a breaking stress, when I discuss that breaking stress is equals to breaking force divided by area. So I must say that breaking stress is material dependent property, and does not it does not depend on the dimensions of object. That means when I say dimensions, it means not even on the length or not even on the cross sectional area. But the question is, breaking force breaking force depends on the shape and size of an object. So when I'm talking about the braking force, it depends on the shape and size of the object. But braking stress, it is the material dependent property. So what I mean is, let's have a question based on that, and that will teach me the correct concept. Let's suppose this is one of the wire, and this is having a length of 10 meter, and its cross sectional area is 10 centimeter square. It is made up from the aluminum. Let's suppose this is another wire. This is again having a length of 10 meter, but its cross sectional area, let's call it A1. This is A2. This is equals to 20 centimeter square. Again it has been made up from the aluminum. So the question is, find out ratio of breaking stress of both the wires. So if I look for the breaking stress of both the wires, I must look at the material. If material is same, it is same. You don't need to see anything else. So it's a breaking stress of first wire divided by breaking stress of second wire. It is equals to 1 is to 1. Why? Because material is same. I hope this is clear. But now let's suppose I have been asked about the ratio of the breaking force. If I have been asked about the breaking force, so I understood that breaking stress is equals to breaking force divided by area. As I know both are having the same breaking stress, so it's a breaking force of first divided by area of 1 is equals to breaking force of 2 divided by area 2. So this is breaking force of 1 divided by breaking force of 2. That should be is equals to area of 1 divided by area of 2. Area of 1, this is breaking force 1 divided by breaking force 2. This is 10 centimeter square. Both are a ratio and having same dimension, so no need to convert it. It's a 10 by 20. This is equals to 1 is to 2. So their breaking forces are different. Their breaking forces are different if the dimensions are different. Here the cross sectional area has been the different, but breaking force is different. Breaking stress would remain the same. So please do remember this. This is the very important statements that breaking stress is material dependent property, and it is not going to depend on the dimensions of the object. But breaking force definitely depends on the shape and size of an object. If if cross sectional area is different, breaking force is different. But if cross sectional area is same, it is going to be same. I hope this is clear. Is it clear? Let's work for the next question. Let's suppose we have a one of the wire having length is equals to 40 centimeter. The question says if we cut this wire in, let's say, four different wires of equal length, find out new breaking stress of the wire. So this is the situation. Initially breaking stress 1, let's call it x newton per meter square. Now what I have done is that this was the wire and I have divided this into four segments: first, second, third and fourth. Let's understood this is the equal length wires, and this is the, let's suppose I have chosen any one of the section. Then lengthwise it was 10 centimeter. What I need to do, I need to find out the breaking stress of this wire. So one thing is for sure, they have asked me the breaking stress. And it depends on the material. If you cut this wire, it is not going to change its length. I hope you understand this. That if you are going to cut this wire, it is not going to change its length. And if it is not going to change its length, that means breaking stress would remain the same. So breaking stress of new wires, if you pick any of them, it will be again x newton per meter square, because the material material remains same. I hope this is clear. Is it clear? Is it clear? So please don't make a mistake. Always go with the questions, go through question in very calm situation, because once you have read a breaking stress to breaking force or breaking force to breaking stress, it will made a mistake. I hope this is clear. So please go through the question, give a time to the question. Yes, read it properly and with very calm mind, and then go for it, that whether they have asked breaking stress or whether they have asked breaking force. Let's look at the next question. The next question says that the maximum stress which the wire can bear is called as the breaking stress. Yes, this is breaking stress. Next, the substances that can be stretched to the large values of the blank are called as the elastomers. Yes, they are the substances that can be stretched to the large values of the strain are called as the elastomers. Let's look at the next question quickly. In the if the elastic region is quite large, the material does not obey the Hooke's law. Basically, they are the elastomers. Their elastic regions are very much higher, and when their elastic regions are very much higher, they are not going to follow Hooke's law. Next, the ratio of the stress and the strain is called as it is the modulus of elasticity. It is the ratio of the stress to the strain. This is modulus of elasticity. So, I hope this is clear up till now. Is it clear? Is it clear up till now? Do you have any doubts? Is there anything? Is there anything? Are you sure? Can we switch to the next topic? Let's begin. Now we are going to discuss a third important parameter of the solids, that is modulus of elasticity. We have already covered stress, in the previous class. Then we have switched to the strain in the same class. And now it's a third important parameter. It's a modulus of elasticity. So after understanding of this, we will understand uh, a larger amount of data about the solids. So let's begin. What modulus of elasticity and what are the different types of modulus of elasticity? Basically, when I say it's an elastic moduli, it is the ratio of the stress and strain. So when I take a ratio of any stress and strain, then it is called as a modulus of elasticity. We have three types of modulus of elasticity. One is the Young's modulus, another is the bulk modulus, generally denoted as B, but some authors write it as an K, and modulus of rigidity. It's a modulus of rigidity, that is N. So first, we are going to discuss about the Young's modulus, and then by process we will move to the next two. So let's understand what Young's modulus is. Let's understood that, and look at this diagram. We can see that one end of the wire is fixed to the top with rigid support, and stretching force F is applied. Normally it's a perpendicular to its faces as shown on the figure. Let's understood that length of the wire is L, and the cross sectional area of this wire is A. So when I'm going to apply this force, that due to the stretching force, the length of the wire, initially it was L, now it is L plus delta L. So there is a change in the length of the wire, and this change in the length of the wire is delta L. So if I write down the stress to the strain, then I could say it's a longitudinal stress, which is a force per unit area because it has been acted perpendicularly. And the longitudinal strain, basically it's a change in dimension to the original dimension. This is equals to delta L by L. So this Young's modulus that could be written as, this is longitudinal stress to the longitudinal strain. And when I say it's a longitudinal stress to the longitudinal strain, this is equals to longitudinal strain could be given as F by A, but longitudinal strain could be given in delta L by L. So if I take a ratio of this, this could be written as, this is FL by A delta L. If force is treated as an mg, then this is equals to mg by area could be pi r square divided by delta L into L. So this is, in this situation, this could be written as, this is mg into L divided by pi r square into delta L. I hope this is clear. Is it clear? It's SI unit. If you look at on a purpose of units, then this is unitless. It's a delta L by L. So only this term is having unit. It's a force by area. That means a Newton per meter square, or we can say it's a Pascal. CGS unit. CGS unit of Young's modulus, it's a dyne per centimeter square. And the dimensional formula of this, it's an m1 L minus 1 T minus 2 that we have derived. I hope this is clear. So do you understand Young's modulus up till now? Is there everything clear? Is there everything clear? Are you sure? Are you sure? Basically, it's a ratio of the stress to the strain. So let's look at certain quick questions and we will move forward to this lecture. The unit for Young's modulus of elasticity. Yes, it's a Newton per meter square. Next, the dimensional formula. The dimensional formula for Young's modulus of elasticity is, it is m1 L minus 1 T minus 2. Next, Young's modulus of wire. Depends on the acceleration due to gravity. No. It depends on the length. No. It depends on the area of cross section. No. It depends on the material of the wire. Yes, there are other factors too. On which it depends. But one thing is for sure, that if you observe a formula very carefully, then it's in Young's modulus, that is equals to stress divided by strain. But it doesn't mean that Young's modulus is directly proportional to the stress, or Young's modulus is inversely proportional to the strain. No, this is absolutely incorrect. You could not think like this. This is incorrect. This Young's modulus is material dependent property. It is material dependent property. So if you want to change the Young's modulus, if you want to change the Young's modulus, just change the material. It will change the Young's modulus. I hope this is clear. This is clear. But by changing the stress, you are not going to change it. If you change the stress, and it if you increase the stress, and it will increase this Young's modulus, and if you decrease the strain, it will decrease or increase the strain. No, this is not the case. I hope this is clear. Is it clear? Is it clear up till now? Do you understand this completely? Are you sure? Are you sure with this? Are you sure? Great. Now let's discuss the factors on which elasticity depend. Elasticity depends. Yes, I'm talking about the at this point of time I'm talking about the Young's modulus, that if if temperature increases, if temperature increases, elasticity decreases. Elasticity decreases. So if we are going to increase the temperature, it's a temperature increases, this is going to be decrease. So in reality, I could not say that Young's modulus is decreases, because Young's modulus is a fix for every material. But it does have an effect of temperature, that when and when temperature increases, elasticity elasticity of every material decreases. Next, if we add an impurity, if we add an impurity, then elasticity of material may increase or decrease. How this can be identified, that what will happen if whether it is going to increase or whether it is going to decrease. So let's suppose, understand this for the this is considered as an understanding purpose only, that let's suppose this material is having, let's suppose elasticity y as an x Newton per meter square, and I'm going to add this block as an impurity, and this block is having an impurity of, let's suppose, p Newton per meter square. So after this is added, this will be something like this. This block is having impurity of x plus p. So it is the material which supports the elasticity. But if certain materials has been added which is having very less elasticity, that means let's understood this by this is having a less elasticity, and to represent the less elasticity I represent it as a minus of q. So after this addition, this block will look like something like this. This has been added, and this new y dash would be x minus of q. This is for understanding purpose only. Please do not write it in your examination. This you need to write only this much in examination. Yes, so if we add an impurity, then elasticity of the material may increases or decreases. Next, if we are hitting the materials, if we are hitting the materials that we call as an, if we hammer the material, if we hammer the material, it will increase, it will increase the elasticity, it will increase the elasticity of material. So young elasticity will increases by hammering the material, because it will convert a large granules into a smaller granules. And when you are going to convert your large granules to a smaller granules, it will it will increase the elasticity of a material. Next, in an annealing process, in an annealing process, do you understand what annealing process is? It is repeatedly make a body to a colder region, shift a body to a hotter region, and do this continuously and for very long amount of time, that make it colder, make it hotter, make it colder, make it colder, and something like this. This is the annealing process. In an annealing process, elasticity of material decreases. So in the case, it's a decreases. In the case of the in annealing process, it is going to be decreased. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts up till now? Is there anything? Is there anything? Do you have any doubts? Are you sure? Are you sure? Done? Great. So now ready for the questions? Let's suppose, let's suppose we have two wires. This is having length L, a cross sectional area A, and let's write it over here. It is having cross sectional area A, and it is going to be hanged, it is going to be pulled by a force of, let's say it's a 2 into 10 to the power 3 Newton, and this is the another root. Again the length will be the same, a cross sectional area again same, but it has been pulled by 4 into 10 to the power 3 Newton. What I need to ask, I need to ask that delta L1 it's so delta L2. They have given that find ratio of, find ratio of delta L1 to delta L2 if this both are made up from same material. If they have been made up from the same material, you need to find out the delta L1 is to delta L2. So when they say us that they have been made up from the same material, when this is to be declared that they have been made up from the same material, one thing for sure, that their Young's modulus are equal. From the diagram I can see that their lengths are equal, their cross sectional areas are equal. So when and when this kind of question arise, always make a formula that it's a y is equals to f L divided by a delta L. Now in this look at this, y is same, length is same, cross sectional area is same, only the things that has been changed is f and delta L. So do not everything write on the boards, always write it's an f directly proportional to the delta L. Always think like this will help us to get it done very easily, because here I have not mentioned the length, I have not mentioned the cross sectional area with its value, I have just shown it with a diagram. In the examination hall it would be happen that there would be a number of this. So when and when you are going to write whole number, and if you are going to take the ratio of this, this will become a bulkier, and when it is a bulkier, there is a probability to get it incorrect. So always look that which parameters are changing. If they are going to change some more parameters, to write it down, but if not, then only write those parameters which are changing or which are different to each other. So this is f1 by f2, which is equals to delta l1 to delta l2. So it's a delta l1 by delta l2. This is equals to f1. It's a 2 into 10 to the power 3. This is 4 into 10 to the power 3. This has gone, and this is equals to 1 by 2. This is delta l1 is to delta l2. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts up till now? Is there anything? No? Ready for the next question? Let's have a look. The next question is one of the favorite questions of all the faculties, and that's why they ask in the examinations, that they will say that if a wire is stretched by T1, then length of the wire is L1. Now, if wire is stretched by T2, then length of the wire is L2. They will ask find natural length of wire. So go through the data very carefully. Have you read it? Have you? They said that if a wire is being stretched, that's, let's suppose this may be the situation. This was the natural length of the wire. Let's call it L. And if I'm going to stretch it by certain force T1, then this wire should look alike something like this. This is the case of T1, and this is the length L1. And when it has been stretched by some other force, it would be the length of L2. This is the length of L2, and this has been applied by force T2. This was the natural. I hope this is clear. So what I'm supposed to do is, first thing is for sure that their Young's modulus in both the situations will remain the same, because material is not going to change. It is the same wire that we have stretched in two separate mechanisms. So first thing, y1 equals to y2. Now what is y1? It is basically f1 l1 divided by a1 delta l1. This is equals to f2 l2 divided by a2 delta l2. I hope this is clear. So even the cross sectional area remains the same. So a1 equals to a2. Cut it down. Now what do you want? You want the natural length of the wire. What is force 1? It's a T1. Original length of the wire, it's an L. Divide by delta L, which is a change in length. This will be L1 minus of L. This is equals to new force, it's a 2. Original length, it's an L. Divide by delta L, that delta L was L2 minus L. So the situation is that it's a T1 into L divided by L1 minus L is equals to T2 into L divided by L2 minus L. So this L and this L has gone. So I have been left with this much number. It's a T1 into bracket L1 minus L. This is equals to T2 divided by L2 minus L. So this is T1 into bracket L2 minus L. That is equals to T2 into bracket L1 minus L. So this is T1 L2 minus of T1L. This is equals to T2L1 minus of T2 into L. So from this it could be written as that this is T1L2. This is T1L2 minus of T2L1. This should be is equals to T1L minus of T2L. So from this L as a common. This is T1 minus T2 and this is T1 L2 minus of T2 L1. So this is L, that is equals to T1 L2 minus T2 L1 divide by T1 minus T2. This is the natural length of the wire. This is one of the very famous question. This is one of the very famous question of Young's modulus. I hope this is clear. Is it clear? Is it clear? Are you sure? Even this can be asked. Even this question can be asked in this situation. Let's understood this question. That let's suppose one of the road is there. It's having length L, cross sectional area A. Now let's suppose it has with the road one of the mass has been hung, and this will be the M1. Now the new length will be L1. Now in the next situation what I'm supposed to do is that now it is having this M1 and M2 both. Now the length, it is the same route. Now the length will be L2. I hope this is clear. This length is L, this cross sectional area is A. It is the same route. So they will ask me find out natural length of wire. This will be the question. I hope you can do this. You don't need to do anything extra. What you need to do is that replace this T1 with M1G, that your now force with which you are going to pulling it, it's an M1G, and this in this case it's an M1 plus M2G. That's it. It is the same thing, but you must do it. I'm not going to do this for you. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Now let's look at this question. In this question, they have given a graph of, it is a graph of stress versus strain, and they have plotted this graph for two different wires. One of them is the A, one of them is the B, and they will ask me that which wire is at higher temperature. So this would be their question. How will you identify this? What is to be done? What do you think? So when I understood that this is the graph of the stress versus strain, if I take a ratio of this, when I say it's a ratio, it means we are going to take a slope of it. If I going to, if we are having a slope of it, then slope of the stress versus strain graph is the Young's modulus. And you understand that to find out the slope, we have two options. It's a theta A and theta B. It is something like this. And as I can understood that as theta of B is greater than theta of A, that means Young's modulus of B material is greater than Young's modulus of A material. Now one more thing that I understood, that we have discussed that on the factors that affects the elasticity of a material, that if Young's modulus is higher, its temperature would be lower, or as soon as we are going to increase the temperature, as soon as we are going to increase the temperature, its modulus, its elasticity starts decreasing. So as YB is greater than YA, that means T of B, it's a temperature of B is less than temperature at A. I hope this is clear. Is it clear? Is it? Is it? A same kind of questions can be asked. Only the things they are going to change is on the dimensions, on the axis they are going to change the things. It's a strain versus stress graph. Let's say this is the strain versus stress graph, and again two wires would be there. This would be, let's say, A, this would be the B. They will ask the same thing, find out which wire is at higher temperature. So this is the requirement. This is the requirement. You need to find out that which wire is at higher temperature. So now basically it's on the y-axis it is strain, and on the x-axis it's a strain. So if I take, it's a y by x, it's a y by x, that means if I take the ratio of the strain to the stress, basically it is 1 by Young's modulus. So if I find it out the angle of this, it's a theta A, let's say this is theta B, then as I understand that theta B is greater than theta A, that means here the slope is not the Young's modulus, here the slope is 1 by Young's modulus. So when I say the slope is 1 by Young's modulus, this is the situation, it's a 1 by y of B is greater than 1 by y of A. That means y of A is greater than y of B. And if this is the situation that y of A is greater than y of B, that means T of A would be less than T of B. It's a temperature of wire A would be less than the temperature of wire B. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. So ready for the next question? Are you ready? Let's have a look. Let's suppose the situation is that this is a rigid support, and with this rigid support a wire has been hung, and with this wire I have attached a certain load. This load is having mass m1, this wire is having mass m, it is having length l, and its cross sectional area is the A. Now what I need to do is let's suppose we have a location, this is point over here, and this is a distance x from the bottom end. So they will ask me that find out longitudinal stress acting at point P. This is point P as shown in the figure. How will you do this? So what I need to do is basically I need a stress. It's a longitudinal stress, and when I work for longitudinal stress, this is equals to force divided by area. So at this point what is the force that is acting? So if I understood that, basically I need to find out the tension at that point. To find out the tension, that is I have written over here as a force. What I need to do is this m1g is the fix. Now I need to write down the tension due to this rod and only on this point. So what I'm going to have is it's a total mass m divided by total length l multiplied by the length that you have used. It's an x into g plus this m1g. This is the tension, this is the force acting at this point P. So this longitudinal stress, that would be equals to m by l into x into g plus m1g divide by its cross sectional area, it would be an A. This is the stress acting at point P. I hope this is clear. Is it clear? Is it? So do you understand each thing, everything? Are you sure? Do you have any doubts? Is there anything? Is there anything? Are you sure? Are you? Do you have any doubts? Is there anything? Is there? No? Great. So can we move to the next point? Let's look at this. It is elongation of a wire due to its own weight. This is the elongation of a wire due to its own weight. So let's suppose understood that weight of the wire mg acts at the center of the gravity of the wire, so that the length of the wire which is stretch, that would be equals to L by 2. So this is the one of the wire, and it is having, let's say, mass m, and it is having length L. And if I apply a Young's modulus here, then it's a y is equals to FL by A delta L. When I take L, it would be at, it has been taken from here, because a total mass of this wire is going to be concentrated over here. So it's an FL by 2 into AY. When I write F, it was the MGL divided by 2AY. This is M into G into L divided by 2AY. This is the elongation of a wire due to its own weight. I hope this is clear. Now one more form of this is when I am going to replace this M with density and volume, then that could be that could be written as, this mass could be written as, it's an A into L into D into G into L divided by 2AY. This AA could be gone, and this L and this L would be the L square into density into G divided by 2Y. This is the elongation due to its own weight. So first, always you need to consider that this is the situation where you are going to take your mass at the center of mass, because total mass of that body is concentrated over that point. I hope this is clear. So this delta L would be equals to mgl divided by 2ay. Or if I replace this m, this could be written as, it's a density into volume, it's a area into length into G into L divided by 2 into A into Y. This 2 has gone, and this is equals to rho G L square divided by 2y. This is delta L. If I want to plot this for the delta L versus L square for this relation, then it could be written as, this is, let's say, delta L, this is L, as it is, everything other than this is constant. Let's put it into one of the bracket. So this is delta L, this is L square. It's a delta L is having a power of 1, L is having power of 2. So it is going to something like this. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Is there anything? No? Great. So let's wind it up this session over here. But before we wind it up, I would like to have two of the quick questions. Let's have a look. It's an aim of Searle's experiment is to find, a Searle is a scientist who has performed an experiment to find out the Young's modulus. Please remember this. Next, possible source of error in Searle's experiment is that twist in the wire. Yes, support may be bent, could be error due to temperature, or this all could be the possible source of error in Searle's experiment. So let's wind it up this session over here. This was all about the Hooke's law, and from the Hooke's law, we have begin the Young's modulus, and we have discussed what elasticity is, and we have seen all the variations of this. Please go through this very carefully. This is going to help us a lot to crack the examinations. Thank you. Have a good day. Take care.